Do 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 do. Welcome to our second video on Newton's laws. So, unsurprisingly, the first video on Newton's laws was about Newton's first law, and the second video on Newton's laws is on Newton's second law. So if we just remember quickly, Newton's first law said that an object at rest will stay at rest, or an object in motion will stay in motion, unless acted upon by a net force that was not equal to zero. In other words, if all of forces were balanced, it wouldn't speed up or it wouldn't slow down. Its acceleration would be zero and its velocity would be zero. If it's not moving, it would be zero. If it is moving, it would stay at a constant velocity. So let's keep that in mind and see how that compares to Newton's second law. So Newton's second law here right away is different. If a net force, so we have a net force now, so all the forces added up are not going to equal zero, is applied to an object, it will accelerate, the object will accelerate, at a rate proportional to the net force applied and inversely proportional to its mass. So what is this actually saying? So it says if a net force, so we write net force, say the sum of the forces is not equal to zero. So if all the forces added up does not equal zero, is applied to an object, it will accelerate. So this is new. So acceleration will also not be zero. At a rate, all right, this is the part that talks about how that's going to accelerate. Proportional to the net force and inversely proportional to its mass. So let's take a look. What does this actually mean if we write this out in a formulaic way? So it will accelerate at a rate. So we're going to say A equals, now proportional to the net force. So that just means if one goes up, the other goes up. If one goes down, the other goes down. So we're just going to say equals to the net force. And in this case, we're going to multiply inversely proportional to its mass. So inversely proportional means instead of if one going up, the other goes up, inversely proportional means if one goes up, the other goes down, or vice versa. So the way that we write an inversely proportional, just like inverse, is 1 over inversely proportional to its mass, so 1 over m. If we combine these together, we get A equals sum of the forces, and we could write this over 1. So you multiply the tops and you multiply the bottoms, so divided by m. And you guys don't like fractions, so we're going to rearrange this to say the net force equals m times a. And this is our formulation of Newton's second law. And this should look very familiar to something that we were using before, which was Fg equals m times g. This was actually just this was just a version of Newton's second law. The force of gravity is equal to mass times acceleration due to gravity. This was just a very specific example of Newton's second law. So the big thing that we're going to look at here is that the object is going to accelerate. So if all the forces are not balanced, we're going to have an accelerating object. So how do we actually deal with that? So here's an example. What is the acceleration given this situation? So I've drawn on some of the forces, not all of them. So we have a force of gravity acting down, and it's 100 newtons. We have a force being applied to it going to the right of 20 newtons. We have here that mu equals 0. What does that actually tell me? It tells me if, let's just write this down below, if mu equals 0, then friction is also equal to 0, right? Because friction is equal to mu times n. And if this is 0, then this whole thing is 0, right? So we don't have to worry about friction in this question. This box, we're going to assume, if we're not told otherwise, that it's not falling through the floor and it's not starting to float. So we do have a normal force that we should draw on here. Let's label it as N. And what do we know? If it's not accelerating up or down, then that means these two forces have to be equal to each other. So we can actually show that by putting hash marks like this. 2 hash marks and 2 hash marks. That's just shorthand for telling me these are the same. And I can even just go ahead and say this is 100 newtons. That looks a little ugly because we're saying the normal force, and here the N stands for newtons. So just make sure you're being careful with this. So what does this tell me? Let's say, so the question is, what's its acceleration? We've already talked about its vertical acceleration. So in the y direction, so that's vertical, the acceleration was 0. Why? Because the net force in the y direction was 0, right? It would be 100 minus the 100 normal force, right? So that was 100 minus 100 equals 0. So it's not accelerating in the vertical. What about in the horizontal? Well, actually, let's go back up here. In the horizontal, we only have a force acting to the right. There's no friction opposing it, so we don't have a net force of 0. We have a net force of actually 20. Let's write this. Let's see why it's 20. So in the x direction, the sum of the forces is equal to what's pointed to the right was 20 newtons. What's pointed to the left, 0. So the difference is 20 newtons, right? So we actually have an unbalanced force here. So we're going to have acceleration in the x direction. And since that was pointed to the right, it's going to accelerate to the right. So if we want to figure that out, we know the sum of the forces is equal to mass times acceleration. This is Newton's second law. And the question asks us, what is the acceleration? So let's rearrange for acceleration. So we have acceleration equals sum of the forces divided by the mass. Now we know what the sum of the forces in the x direction was. It's 20 newtons, right? So we got that, let's just use a different color. We got that value from here. What about the mass? Are we given the mass in the question? No, we're not. So we need to figure out the mass some other way. And this will be a pretty common thing that you'll end up doing. In order to find the mass here, we need to use the force of gravity. So Fg equals m times g. And if we actually know the force of gravity, it was given in the question, and we know acceleration due to gravity, we can just solve for m. So if I rearrange this, we have m equals Fg divided by g. The force of gravity was 100 newtons. The acceleration due to gravity is 9.81 meters per second squared. And when we do that, we get 10.2 kilograms, which we're going to then just put in here. We're going to use in this formula. You'll find with these questions, there's going to be a lot of finding something one way and plugging it in somewhere else. So let's just show that we plugged this value in here. So let's finish off the question. So 20 divided by 10.2 gives me 1.96 meters per second squared. And does that make sense that it would be a non-zero acceleration? Absolutely, because we only had a force pointed to the right. So this is going to tell us it will accelerate at almost 2 meters per second squared to the right. So how do we tackle these questions in general? So for these dynamics questions, remember dynamics is talking about the movement of objects, but also the y. So we're focusing more on the y here to figure out how they're moving. So for all of these dynamics questions like this, I want you to follow basically this 4-step method. So number 1 is draw a diagram with all forces labeled. This is so key. Do this. Don't think, oh, I know what's going on, I don't need to do this. You have to do this. And most of the times, if you make mistakes, it comes back to you got the forces on your diagram incorrect. So make sure that you spend a lot of time drawing the diagram and making sure all forces are on there and they're all in the right way. Number 2 then, decide which principles apply. So are you going to use Newton's first, or are you going to use Newton's second, or are you going to use both of them? So you may end up having to use both. Write out your equations and then go ahead and solve. So number 1 and 2 are really key. They're sort of setting up what you're going to do to actually solve. I know you guys like to jump right to number 3, but please spend the time doing number 1 and 2. Let's do one more example following these rules. So I've given you a setup here, and I've asked again, similar to the first question, what is the acceleration of this object? So draw a diagram with all forces labeled as step number 1. I do not have all forces labeled. I have my mass here. It's 10 kilograms. It's sitting on the ground. And I have an applied force pointed to the right of 50 newtons. What other forces do we have that are not drawn on here? So you should immediately think, hey, there's gravity pointed down. So Fg. What about pointed up? Well, we're not told otherwise, so we're going to assume that it's not going through the floor and it's not starting to float, so we have the normal force pointed up. And what do we know about these two? They are equivalent to each other. We have mu here, so that is, remember, the coefficient of friction. So that means if this is not 0, there is definitely friction. So if you're trying to push it to the right, friction is going to be a force pointed to the left. So we'll have F here. I believe that's all the forces we need to include here. So number 1 is good. Number 2, decide which principles apply. So are we looking at Newton's first or are we looking at Newton's second? So a couple of keys here. It says what is the acceleration? So that should give you a clue. And we don't know for certain yet, but since it's asking what's the acceleration, I'm going to assume that the friction is going to be less than the applied force. So if these are not equal to each other, we're dealing with Newton's second law. So let's go ahead and see if we can solve for this question using Newton's second law. So Newton's second law is that the sum of the forces is equal to the mass times acceleration. Our question is ultimately asking what's the acceleration, so let's rearrange this to be acceleration equals the sum of the forces divided by the mass. Now, do we know any of these? Yeah, we know the mass is 10 kilograms, so I can fill in the denominator of 10 kilograms. What about the sum of the forces? We're only talking about the horizontal forces here, so we don't need to worry at this point about it accelerating up or down. We're only worried about in the x direction. So what's the sum of the forces in the x direction? Well, I don't know yet, so I'm going to have to solve for that, right? So the sum of the forces in the x direction is going to be F, the one given to us, minus the force of friction. So we know this, right? We know this is 50 newtons minus, do we know friction? No, not yet. So we're going to have to solve for friction. You can see how we are going to solve for one thing to get something else to get something else. So for friction, it's mu times n, or the fun formula. Do we know what mu is? Yeah, it was given to us in the question. It is 0.25 times the normal force. Do I know the normal force? No. Keep going. What's the normal force? Well, we said, unless we're otherwise told, the normal force is equal to the force of gravity. They're balanced. So we know that the normal force is equal to the force of gravity. Do I know the force of gravity? No, but I can find it. How do we find the force of gravity? We do mass times acceleration due to gravity. And at this point, I think we're, as deep down the rabbit hole as we need to go. I think we can solve this to plug into here, to plug into here, to plug into here to get our final answer. So let's see if we can do this. So our mass was 10 kilograms times acceleration due to gravity, 9.81 meters per second squared. Don't need to pick up a calculator, just move the decimal, 98.1 newtons. That is going to go, right here, because that's our normal force. So 98.1 times 0.25, what does that give me? I'm actually going to have to pick up my calculator here, times 0.25, gives me 24.5 newtons. All right, what are we doing with that number? Why'd we bother getting that? Because we're going to substitute that right into here. because that's the force of friction. So we have 24.5 newtons. 50 minus 24.5. Remember, you can use your calculator so that we don't round until the very final answer. If you just put in 50, subtract, and then hit your answer button, it should plug in that 24.5 but unrounded. And when you hit equals, it gives you 25.475 newtons. Why did we need to know that? Well, that's our some of our forces in our x direction. That gets plugged into here. So we have 25.475 newtons divided by 10 kilograms. Again, I just need to move the decimal, so I have 2.5. And I think we're dealing with, what, 2 significant digits? Let's go with 2. We'll pretend like there was a decimal here and there was a decimal here. So 2, 2, 2. So 2 significant digits gives me 2.5 newtons per kilogram, or when you do all your unit cancellation, you get meters per second squared. So the acceleration is 2.5 meters per second squared. So you can really see it's really important to set up your diagram and then choose whether you're using Newton's first or Newton's second or both, because everything flows from that. Once we decided it was Newton's second, we figured we needed to find this by doing this step. In order to do this, we needed to do this step. In order to do this, we needed to do this step. And it all hinged on whether we put in all of our forces correctly or not. So you can see you're going to have to do a lot of work and use the numbers in one calculation somewhere else, which then might get used somewhere else, and so on and so forth. So it's easy enough to make a little mistakes. Make sure the mistakes you're making are calculation errors, if anything, just punching something into your calculator incorrectly, rather than an error with your setup of your diagram.